As Gary said, I'm with the Kansas Geological Survey, University of Kansas, and we have just some intro, we have no regulatory or policy-making function. Our job, to cut to the chase, is to provide a sound scientific foundation for decision-making related to natural resources issues in the state of Kansas. And that's what we do. I'm in the geohydrology or groundwater section of the survey. So not surprisingly, I spend a lot of my time working on the High Plains Aquifer. Now, Gary asked me to talk about some of the things we're doing, and what I'm going to try to do is focus on a portion of the aquifer that should be of some relevance to the audience here. So let me get rolling, if I can get everything working yet. High Plains Aquifer, I think most of you guys know what I'm talking about. Covers portions of 8 states in the central United States. One of the largest and most important aquifers, not just in our country, but in the world, because of the critically important agricultural production that it supports. So I've got this inset showing the aquifer within Kansas. Let's expand that. And in Kansas, we divide the High Plains Aquifer into 3 kind of sub-components. There in the far west, we have what we call the Ogallala Aquifer. And this is what I'm going to focus on in my presentation today, because this obviously extends down to the Oklahoma Panhandle. So I think the results that we're getting there will have some relevance to y'all. There's also another component there south of the town of Great Bend, named for the Great Bend of the Arkansas River. Now, we got that pronunciation right, y'all. I know based on discussions I've heard today that most people favor another pronunciation. That's all fine and good. But when you do so, remember, that's pronunciation by legislative edict. Okay? You're basically doing what the man tells you to do. That's not the way we live in Kansas. Okay, so let's continue. So that's the Great Bend Prairie. Then just north of Wichita, we have the Aquifer beds. So I'm going to focus on the Ogallala. So the obvious question is, how are things going out there? Well, I'm sure the same as can be said for the Oklahoma Panhandle. The aquifer in western Kansas, the Ogallala Aquifer, is under stress. Now I'm going to show you a couple of different pictures to give you a feel for that stress. Let me see if this animation will work. But this is 1996 to present, showing the cumulative declines in water level within the aquifer. Focus there in western Kansas, particularly southwest Kansas, where we're getting very large declines exceeding 60, 70 feet from 96 to present. And so you can see that goes into the Oklahoma Panhandle as well. So clearly this system is under stress because of the pumping that's going on there. So this is 96 to present. We can look at a longer term view. This is percent change in aquifer thickness or saturated thickness since the onset of wide-scale pumping for irrigation, since what we call pre-development, so we're talking the 40s and 50s. And what you'll see here, looking at the map, the red colors is where we've lost 30, 45, even 60+% of the aquifer is gone. So you can see in certain areas of Kansas, we are in relatively dire straits. Now those blue areas, there in northwest Kansas, those are just anomalies, very thin saturated thicknesses that aren't used, they're not of economic importance. So when we look at the Ogallala, we're seeing significant declines have occurred. The thickness of the aquifer has significantly diminished. Well, what's the impact? Well, as that aquifer thickness diminishes, the ability of the aquifer to readily yield water to wells diminishes. So well yields diminish. The depth to water increases, making it more expensive to bring the water to the surface. These factors put stress on the agricultural community out there in western Kansas and probably the Oklahoma Panhandle as well. Now, this is clear impacts, but there are some additional impacts I just wanted to mention as well. Some what I'd consider as collateral damage, and that's the impact on our surface waters. Because in western Kansas, the rivers and streams were primarily groundwater fed. The water table pre-development was above the bottom of the stream beds, so water flowed from the aquifer into the streams. Widespread pumping has changed that situation. So I've got this schematic here. The top is the major perennial streams in Kansas in '61, before we really begun to feel the impact of the irrigation pumping and the lowering of the water table. The lower one is '94, and we've done, there's a more current map. I didn't have time to bring it in for today's presentation, but the situation has deteriorated even further since this '94 map. You can see that lowering of the water table, taking it below the bottom of the streams, has caused many of our rivers and streams in western Kansas just to stop flowing. Transition from a perennial stream to, at best, an ephemeral one. So I just wanted to give you a picture of what that looks like. We'll go on, we've got a research site on the Arkansas River just downstream of the confluence with the Pawnee at the town of Larned in south central Kansas. And here's a picture. We've been at this site since 2001. This is a picture of the Arkansas River, one of the major rivers of the state, on a pretty good day since 2001. Most of the time, from the same vantage point, what you get is this. Basically, just bone-dried sand and gravel riverbed. Now in this shot, the riparian community here is still doing pretty well. This is the cottonwoods, the willows, the mulberries, but their health waxes and wanes with the depths of the water table because they're phreatophytes, they're tapping groundwater for the water supply. As you go upstream on the Arkansas River channel, you begin to see a different picture in terms of the riparian zone vegetation, and there's just carcasses of our cottonwood, willows, etc. Even the salt cedar, the tamarisk, has difficulty when the water table drops below a certain distance from the land surface. So, current conditions out west, the Ogallala Aquifer in Kansas, are not particularly uplifting. Let me just to try to get a little, bring a little humor into it, let me note that the Arkansas River is one of 3 rivers in the state of Kansas that's legally classified as navigable. Now, obviously, that's now via the ATV mechanism there. But anyway, so current conditions are not particularly uplifting. And so what we've been asked at the survey to do is try to say, what are the future prospects for this area? What does the future hold for the High Plains Aquifer in western Kansas, and probably pretty similar in the Oklahoma Panhandle? Well, for Kansas, Tracy Streeter, the director of the Kansas Water Office, gave a presentation yesterday afternoon. I'm betting Tracy's somewhere here in the audience. Okay, I've got him located, so if questions are asked, I can send them to him. What Tracy talked about, probably in passing, were some of the efforts that we're doing to try to get a handle of where we're going with the High Plains Aquifer. And this involves these groundwater models that we've been creating for western and south central Kansas. Now, when we're looking at future prospects, we work within the framework of kind of groundwater management framework within the state of Kansas. And what we have are groundwater management districts in the High Plains Aquifer. Now in Kansas, the Division of Water Resources of the Kansas Department of Agriculture is in charge of water management, whether it's surfaced or groundwater. and there's a chief engineer of the Division of Water Resources that makes decisions about water rights, etc. And out west in High Plains Aquifer, the Division of Water Resources is assisted by groundwater management districts. These are kind of local vehicles for having some local control in the groundwater management mix. So they can have suggestions for managing their water, within the framework of Kansas water law. And they have elected boards. You have to be a landowner, rural landowner of at least 40 contiguous acres, or you've got to be a groundwater user of at least 1 acre-foot per year. But we work within this framework. So we construct groundwater models, we and others, for each of these groundwater management districts. And one of the things Tracer may have mentioned yesterday is we're trying to unite all these models, to link them together so that we can get a better picture of what the future holds. And at the Kansas Geological Survey, we're working with each of these management districts in one way or another. So we've got these groundwater management districts. They're looking to us for answers to questions what the future holds. Now, if you're going to answer that question or begin to address it, let me rephrase that. There's something you got to have. And you've got to have information about current conditions in the system, in the aquifer, and what's happened in the past. In other words, you've got to have some data. This is how we make the sound scientific decisions. We've got to have the data to back them up. So let me show you what we have in Kansas. We've got a couple things. I'm going to focus on 3 elements of our data collection. We have an annual water measurement and water level and water use program for decades within Kansas. Every January, the Kansas Geological Survey, and prior to us, the United States Geological Survey, in concert with the Division of Water Resources, the Kansas Department of Ag, we go out and measure water levels in approximately 1,400 wells across the High Plains Aquifer each January. The idea, do it in January, the pump's on operating, you're a few months past the cessation of the irrigation season, so how pumping was distributed through that irrigation season has a relatively limited impact on that water level measurement in January. So we've done that for decades in Kansas. And those maps that you saw earlier were all created using this data set, approximately 1,400 measurements per year. But that's not enough. That's showing us how the water levels are changing. But we got to have information as well as what was the factor that induced those changes. How much pumping is going on out there? That's the key element. You got to have both the water level change and the water use if you're going to be effective and be able to address issues about what the future holds. So what we've got in Kansas, we've got water rights. We use the priority system in water rights. Senior guy trumps everyone, this sort of thing. Every non-domestic well with a water right has got to have a totalizing flow meter. And what you're seeing here is the red dots are the non-domestic wells with water rights in the High Plains Aquifer, and then some alluvial aquifers you'll see as well. In the High Plains Aquifer, closing in on 32,000 wells with totalizing flow meters. So we have got a good handle on how much pumping is going on. And so with that combo, the water level changes, the water use, we can say things that others have great difficulty in getting at because of the foresight of my predecessors to get that data that is so critical. And in Kansas, we started going with totalizing flow meters in 1980 in certain of the groundwater management districts. So it varied across the groundwater management districts in terms of how rapidly the transition from no meters or from duration of pumping meters to the totalizing flow meters. But this is one heck of an important data set that we can use. Now, we also, those are annual measurements. We also have a series of monitoring wells at which we're obtaining continuous measurements. These have water level measurement devices, taking measurements every 30 minutes to 2 hours, depending on the site, sending it out via telemetry. It's on the web for folks to see. Right now we've got 8 wells that are out there that kind of represent different portions of the High Plains Aquifer, focused on the Ogallala. Gives us information about how the aquifer responds to active pumping, something that is not always totally clear from once-a-year measurements. So this gives us a lot of information about what the future holds for different portions of the aquifer out there in western Kansas. And right now, I said we have 8 wells. We've got another 4 to 5 that will be coming on in the next 4 to 5 months, and I expect this to expand even more. And all this via telemetries on the web so folks can get a feel for how the aquifer is doing in their area. We also have an equal number of wells where we have to go manually download the continuous sensor simply because of cost involved. So we've got all this data. And keeping these programs going, just the data collection element, as many of you in this room, for example, the folks who work in the Mesonet, which is a great system, and we cannot touch that in Kansas. We are just so impressed with the Oklahoma Mesonet system. But keeping these systems going is quite an effort. So there's often an inclination to say, heck, you know, this is all the effort I can spend on this. I'm just taking all this information and putting it in some file. And what we need to be doing is really analyzing these data as they come in, because they have we can glean a lot of insights about what's going on and what the future holds by doing so. But that's oftentimes a difficult activity to convince people that we should be spending time on that. And what I wanted to do was show you, if you have just simple annual water level measurements, annual water use, what you can do with it. I mean, I've talked about these groundwater models that we have, and I think many of you are familiar with those. But we've recently come up with a new approach using these data sets that we have to extract more information about the aquifer. In particular, when we were doing these kind of, I guess you'd say, data analyses, we're taking the water level and water use data and fooling around with them, what we noted was that when we plotted annual water level change versus annual water use, it plotted as a straight line, regardless if we are up there in northwest Kansas in Groundwater Management District 4, or down there in southwest Kansas in Groundwater Management Districts 2 and 5. And we realized this cannot be serendipity. There has to be an underlying physics base to this. So that led us late last year to develop a theoretical framework to analyze these data based on a simple water balance. And we realized that linear relationships on these plots is what theory would predict. And if we look at the slope and intercept of a straight line, we fit this linear relationship, we can get valuable information just there right away about the aquifer. And I just wanted to demonstrate that real fast with Groundwater Management District 4. I chose that for Oklahoma because a long-time manager of that district just recently retired. It was Wayne Bossert, who came out of OU, has worked, I believe, for the Oklahoma Water Board prior to joining Groundwater Management District number 4 in the 70s. In Colby, Kansas, he flew the OU flag come good weather or bad, and that, of course, caused some resentment among some of the inhabitants. But be that as it may, Groundwater Management District 4, what we're going to look at is the data that we have there. Just annual water level data versus annual water use. So on the y-axis here, we've got annual water level change. That's an average based on 182 wells that were measured every year from 96 to January of 2015. On the x-axis, we've got annual water use. That's based on 4,200 wells with totalizing flow meters. You put those together, and you can see that the data fall on an approximate straight line, r squared 0.81. That means 81% of the variability in annual water level change is caused by annual water use. Now, there's noise about these relationships that you would expect. This is the real world. It's not a noise-free world. But the point is the linear relationship. And I should say that in 2007, we had such a huge snow at the turn of the year that we could not get in to take the water level measurements until late February to early April. So I'm just plotting 2006, 2007, taking the average of the two, plotting it as 1 point here. But the bottom line, nice linear relationship. The intercept of that line is how much water is inflowing into the system. You could think of it as the recharge into the system can be calculated directly from the intercept of this line. And that allows us to calculate Q stable. This would be the water use, the pumping over the entire district. They've been pumping at this level, water levels would not have changed. So if the average pumping from 1986 to 2014 had been this amount, the average annual water level change would have been 0. Now, what is the actual average use in that period is 430,000 acre feet. That's only 22%. But that 22% made a difference, resulted in 12 feet of decline on average across the district. We don't have that many 12-foot declines to give up in this area. 22% reduction would have resulted in stable water levels over that period. Now, where's that water coming from? And because that comes out to about a recharge averaged over the district of 1.3 inches. It's about 3 times what we were expecting. But based on this poster that I saw out here from work using the Mesonet system, it is not, would not be unexpected based on those results shown out in the lobby, an award-winning poster. So it could be that we just didn't get the recharge right. But it also could be that past inefficient irrigation practices, flood irrigation, et cetera, have introduced a slug of water that's making its way through the system down to the water table. And it's been pretty steady since 96, over this 19-year period. But eventually, that's going to run out. That's going to taper off. And in that case, the curves here are going to shift downward. But before showing that, let me just show that in 2014, we seem to be right on the relationship, and that's the 2014 point. But if it's shifting down, how are we going to pick it up? Well, we can't just pick it up in 1 year. We're going to have to revisit this every 4 to 5 years. The 2003 and 2004 points are the points that are most divergent from the line that I'm showing here. So you can't just make too many assumptions based on 1 year. So we're saying every 4 to 5 years we reevaluate and see what the situation is in terms of this quantity Q stable. Because if we have just misestimated recharge and been too low, then there's some very positive ramifications for there in northwest Kansas. If we haven't, if it's just this slug of water moving through the system, we'll see this straight line start moving downward, as you see by these arrows. So the intercept of that line is going to decrease with time. So we'll be able to pick that up. And the idea here is that perhaps we can come into a semi-soft landing. We say, okay, guys, cut 20% now, and then with time, maybe another 20%, ratchet it down as we go. But I think this is a simple approach, theoretically sound, and I think this is accessible to most folks. They can figure out what we're doing here. That I think it's got a lot of potential for us to make some decisions about what's possible in the short to moderate term. And this is of great relevance in Kansas because we have, as Tracy Streeter undoubtedly talked about, we have some new management options out there. The Local Enhanced Management Area option, or the LEMA, was signed into law by Governor Brownback April of 2012. The idea here is that folks and irrigators in an areas, locally generated, irrigators get together and say, hey, we want to cut back pumping our water use by a certain % to preserve this resource for our kids, grandkids, etc. If the majority of folks in the area say that's what we want to do, everybody else has to play ball, then the state, the regulatory agency, comes in and tracks it to make sure that everybody's playing by the rules. So this is this LEMA structure. We had one set up in the circled areas, in the circled area shown. You can see on the bottom right is water level change. There in northwest Kansas is an area of significant water level change, and that was accompanied, you can see in the upper left is an area of higher groundwater use for that portion of the Ogallala Aquifer in Kansas. So this tool that we've developed gives these folks a chance of figuring out how much bang they're going to get for the buck in terms of water use reductions. So I think we're really high on the possibilities here. This local enhanced management area is set up in Sheridan County, what's called Sheridan 6, back in 2013, and 99 square mile area. It looks promising, and we're hopeful that this idea will catch on. There's another kind of variant of it that was signed into law here in April of this year called the Water Conservation Area. The idea here is that folks can come together with less bureaucratic rigmarole, but everybody's got to agree to it. It's not a majority rules as with the LEMA. But I think these management structures are giving folks some options, but the key is we can't tarry too much longer, or our ability to really react to this situation will be limited. So that's all I wanted to say here. I just wanted to give you all kind of an overview about some of the things we're trying to do in Kansas and some of the benefits of what we're trying to do. Major messages. The Ogallala Aquifer, whether we're talking about western Kansas or the Oklahoma Panhandle, is under stress. Significant reductions in saturated thickness has impact on well yields, lifts, and lifts to the surface, so the energy expenses, and of course on our surface waters as well. It's a product of high groundwater use, low natural recharge. However, what we're showing is that practically feasible reductions can make a difference. Now, these may only be short-term stabilizations of water levels. It depends on where this inflow is coming from. And so we at the survey are spending a lot of time trying to nail that down so that we can begin to speak with a little bit more confidence in terms of the timing. And we've got these new management structures that I think should be able to use this concept to their benefit and hopefully extend the lifetime of the Ogallala Aquifer in Kansas. But finally, I just wanted to emphasize that if we're going to make wise, scientific, sound decisions about our natural resources, we need data. And we just can't overemphasize the collection of water level and water use data. You know, Mother Nature is holding the cards here, and we can use data to try to get an inkling of what's in our hand. Without that, we're just guessing in the dark. So I just wanted to emphasize this is critically important. We need the data. And did I just get... Oh, last slide. Whoa. So that's it, folks. Actually, there should be one more slide here. Yeah, that was just a temporary glitch in the system. Just wanted to acknowledge some of my funding sources, our funding sources, my co-authors and I. And I wanted to say one of the missions of the Kansas Survey, obviously, is to get the word out to the public. So we have a variety. We're trying to do this via a variety of mechanisms. including tweets as the Oklahoma Board does, so the Oklahoma Water Resource Institute. One of the things we've done is put together this High Plains Aquifer Atlas, kind of a one-stop shop for folks interested in the High Plains Aquifer in Kansas. You can go on this and get, there's a interactive atlas there on the lower right. So you can go in and click on a well near you and see the record that's been obtained from this 1,400 well measurement program through the years. You can go see the records from these telemetry wells. Just a way to give folks information about the aquifer. And yes, I know what you're thinking. We do have refrigerator magnets, okay? One other thing is we also have these public information circulars that we have about items of particular importance to the state. So just in January, we revised our public information circular on the High Plains Aquifer. It can be downloaded as a PDF. I also have these glossy 6-page publications people can have.